Delaware Tech, Chemistry 100, Chemistry 110, Unit 4 continued, Nomenclature of Ionic Compounds. Let's talk about the nomenclature in general. Nomenclature is a system of naming chemicals, and we're going to be talking about chemicals that are compounds, and therefore compounds have two or more different elements by their definition. But the thing is, there are too many compounds to remember all the names. In fact, to date, there are about 144 million compounds that are known worldwide, and 15,000 of them are added every day. That's about 1 every 6 seconds. So ideally, you want a name or a method of naming that will tell you how many atoms, how many of each atom, and how they're attached if necessary. And this only becomes important when we're talking about larger, more complex molecular or covalent compounds. IUPAC is the organization that determines the rules. This is the International Union of Pure and Applied Chemistry. They make the rules for how to name things, and as well as how to name the elements that go into the various compounds. Any one name that's of a compound should always provide just enough information to give you exactly one formula. Therefore, one formula corresponds to one name, and one name corresponds to one formula. There is no redundancy. So, here's a little algorithm to help you decide which rules you're going to use to name a compound. And we have different rules for ionic compounds versus the molecular/covalent compounds. And the first question you need to ask is, does the compound contain a metal or other cation? Now, we haven't learned about the other cations just yet, so look for a metal. Does it have a metal? Yes, we will use the ionic compound rules. No, we'll use the molecular/covalent rules. Does the cation have more than one oxidation state? Is there more than one possible charge on that metal? If there is, well, you're going to need to tell me which one that is, what charge it is. And the way we do that is with a little parentheses, and we give a Roman numeral that represents the charge. So if the charge was +4, you would give the Roman numeral for 4, IV. And the way you would name the whole ionic compound is you always name the compound by naming the cation, then naming the anion. So if there's only one choice, you just say the name of the metal, which is the name of the cation, and you say the name of the anion. But if there's more than one choice for the cation, you have to tell me which one it is with a Roman numeral. And it's as simple as that. Name the cation, name the anion. For molecular rules, we'll talk about this in the next module, but there you're going to use a prefix to tell me how many of the first element, and then a prefix to tell me how many of the second element, and you just end the second element with the letters IDE. We'll talk about that later. So, let's talk about how to name cations in ionic compounds. There's a systematic way of doing it, and it's actually very easy. If the metal only has one type of cation, it's just the name of the metal. And this is true for groups 1/1A, Roman numeral 1A, group 2, which is also called Roman numeral 2A, group 13, which was known as Roman numeral 3A, and a handful of transition metals. Some transition metals have only one type of cation. Here are a few of them: scandium +3, yttrium +3. The more important ones for you to know are zinc +2, cadmium +2, and silver +1. Silver is Ag. So, for example, if you wanted to name the Na+, that's the sodium ion, and you just have to say sodium ion. There is no number 1 involved. Cadmium +2, cadmium ion. Why? Because sodium has only one choice. In fact, all of the alkali metals, that's the left side except for hydrogen, only form +1 charges when they are involved in compounds. The alkaline earths, which includes calcium and magnesium, only form +2. So there's no need to tell anybody which charge it is, because there's really only one choice. And the same thing for aluminum over in the group 13 elements. Aluminum only forms +3 for the vast majority of time. If there are any unusual compounds which wouldn't be covered in this course, we would actually have to say what they are. If the metal has more than one cation, then you have to tell the person what the cation is. And the way we do that is with Roman numerals. So it's important you know your Roman numerals. 1 through 9. And the reason why 1 through 9 is we really don't have any metals that have charges greater than +9. So the Roman numerals 1, 2, 3, those are easy. The letter I, capital letter I, is a 1, and you add 1, you have 2, you have 3. Roman numeral 5 is a V, and Roman numeral 10, which is not shown here, is an X. And the way the Romans use their Roman numerals, if they put a smaller number, like an I, after a bigger number, like V or X, you added it. So look at number 6. That is V plus I, so that would be 6. 7 is V plus 2 I's, 7. 8 is V plus 3 I's. The only thing left here are number 4 and number 9. If the smaller number, like an I, is before a bigger number, like I is before V in 4 and I is before X in 9, then you subtract the small number from the larger number. So if you look at number 4, IV literally means 1 is subtracted from 5. And IX literally means 1 is subtracted from 10, giving you 9. So, for example, iron plus 2, the Fe plus 2 ion would be called iron 2 ion, or just iron 2. Sn plus 4, that's tin with a positive 4 charge, you would label it as tin 4 ion, or just tin 4. And Cu plus is the copper ion, that is copper 1. So here are a number of examples of cations. Let's see how you do. Remember, if there's only one choice, which is in group 1, group 2, group 13, and a handful of transition metals, you don't need a Roman numeral. All the others need a Roman numeral because they have more than one choice. So use your periodic table. The ones that are the better quality periodic tables will frequently have the charges at the bottom. These are not all the charges, they are the common charges. If you only see one common charge, then you don't need to write a Roman numeral. If you see more than one common charge, it doesn't tell you what charge it is, it just tells you you need to figure out what charge it is and name that charge. So the first one is lithium ion. There's only one choice. Strontium is in the alkaline earths, and they're all +2, so that's strontium ion. We don't need to say it. Scandium is always +3, so it's scandium ion. So these three are always known what their ions are, so there's no need to put a Roman numeral. Whereas iron here, Fe, has a +3 charge. Now I want you to notice I've written the pluses in various different ways, and that's because depending on who's writing them or what textbook or what website you're looking at, a plus charge could be written as just a plus, or a +1, or a 1+. A +2 could be written as a ++, a +2, or a 2+. And a +3 charge could be written as +3, 3+, or +++, though you don't see that very often. So once you're above 3, nobody writes ++++, etc. They just say the number, and sometimes the number's first, sometimes the number's after the plus. It doesn't matter. So in this case, iron has at least 2 possibilities. In fact, we know that iron commonly forms +2 and +3, but I will tell you, even though it's not on your periodic table, iron is also known to form +4 and +5. In this case, it's iron 3. And we would just say iron 3. We don't need to say the plus. Zinc has one choice, zinc ion. Lead is Pb. Remember, plumbing used to be made out of lead pipes, plumbing, Pb, that's lead, +4, so we would just say lead 4 because lead has at least 2 choices. And I noticed that lithium is here twice, so I'll just rewrite it again and go through these. I'll pause here. You can stop it and check yourself. And now I'll show you the answers. So let's look at some names of cations, and now you write what the ion actually is. And this is so much easier. Potassium, there's only one choice. It's K+. Magnesium, an alkaline earth, it's always +2. That's easy. And the ones that have Roman numerals, they tell you what it is. So you just write the symbol and then the plus charge of whatever's in the Roman numeral. So copper +2, chromium +6. Barium is another alkaline earth, just like magnesium and calcium. So that's always +2. Mercury, it tells you +2, so Hg for mercury. Calcium ion, always +2. Iron 3, well, we know what that is. Aluminum, we know, is always +3. Sodium is in one of the alkali metals in the first column, always +1. And lead 4, we just talked about, is Pb +4. So now we know how to name the cations. Let's talk about naming the anions. Simple anions are always the same. And when I say simple anions, I mean anions made of only one kind of atom. So a single atom can have a charge, and we know what charge it is based on its position in the periodic table. But what you should know is whenever you're going to name an anion, we take the name of the atom and we chop off the ending of the atom and we add the letters IDE. So if you see IDE, you know you have an anion. There's no choice. It's always an anion. And sometimes you chop off the INE, like fluorine, chlorine, bromine, iodine. And sometimes you chop off the gen, like hydrogen, oxygen, nitrogen. And sometimes you chop off the eum, like selenium. So if they become negative, they have the ending "ide." So their charge can be found using the periodic table, because you have to ask yourself, based on its position on the periodic table, how many negative charges will make it have a full set of 8 electrons. In other words, how many more jumps do I need to go when I'm approaching a noble gas? Is it -1, like all the halogens, fluorine, chlorine, bromine, iodine? They have to add 1 electron and become -1. Or is it like oxygen and sulfur, which have to add 2, so they become -2, etc. So for instance, fluorine, the name of the atom is fluorine, and we can write it as just F. For the purposes here, I'm going to show you the charge is 0, but you always assume the charge is 0 if it's not written. So it needs 1 more electron to satisfy the octet rule. Therefore, it will form a -1 charge, and we can write that F-, which is the common way to write it, but you could also write F-1. This is fluoride. We chopped off the "ine" and replaced it with "ide." So fluorine becomes fluoride. And you probably heard of fluoride in your toothpaste or in the water to prevent cavities. This is an anion. It has an extra electron. So here are a number of different anions. Let's name them by just chopping off the name of the element and replacing it with IDE. So hydrogen becomes hydride. And remember, this is only for the negatively charged ions. H plus is hydrogen ion because it only forms a +1 charge when it's plus. But when it's minus, it's a -1 charge, and we call that hydride. So we already know fluoride, Cl, chloride, Br, bromide, I-, iodide. And that's how you say it, iodide. And then astatine, when it becomes, that's right below iodine on the periodic table. So you'll notice number 2, 3, 4, 5, and 6 are all halogens. That would be astatide. It used to be astatine, now it's astatide. Next you see the group 6A, which is now called 16. This is the oxygen group, everything below oxygen. So oxygen, these are all going to be -2s because they need 2 more electrons. So we have oxide, sulfur becomes sulfide, selenium becomes selenide, and that's how you say it, selenide. You change the accent. Tellurium becomes telluride. You might have heard of the city in Colorado that's famous for its skiing, Telluride. Polonium becomes polonide, and some of these are more obvious than others. Nitrogen, you should definitely know. Remember, the gen part gets replaced, so it's instead of nitrogen, it's just nitride. Phosphorus becomes phosphide. Arsenic, which will now be -3, will become arsenide. And now we're in the group, so I just went through the -3s. These are the ones under nitrogen. Under carbon, these will, if they gain electrons, they will become -4s. So we have carbon -4, silicon -4, and germanium -4. So carbon would be carbide. You might have heard of an old company called Union Carbide. Silicon, this is an unusual one. It's a little hard to figure out, and at one point I had to look it up. This is silicide. It's not that obvious. Germanium, remember you chop off the ium, so this would be germanide. And the last one, Ga+3. Well, that's gallium, and you might say, oh, it's galide. No, no, no. That's a positive charge. That is a cation. Remember, this was thrown in to trick you. Gallium +3. Gallium only has one choice, so this is just the gallium ion. So now, let's look at the names and write the formulas. Iodide, you're going to need to know where they are in the periodic table, so you're going to always have to have that available. Iodide, and everything below, everything in the same column as iodide, the halogens, fluorine, chlorine, bromine, iodine, astatine, they will all become ides that have a -1 charge. Oxide, oxygen, with -2 charge, and everything below oxygen, so oxide, sulfide, selenide, telluride, polonide are all -2. Everything under nitrogen is a -3, and that includes arsenide. Potassium ion, well, not an ide, so that tells you, oh, it must be a positive charge, and potassium only forms a +1. Remember, potassium is K. Hydride, it's telling you it's the negative version of hydrogen, that's -1, and hydrogen ion tells you it's the positive version of hydrogen, +1. Iron 3, this is iron, this is Fe+3. Telluride, this is under oxygen, so they're all -2s if they're an ide. Selenide, same thing. Chloride, like fluoride and bromide and iodide, are all -1. Magnesium ion, magnesium is a alkaline earth, that is the second column, group 2 or 2A, those are all +2. Just like magnesium and calcium and strontium, those are all +2s. Carbide, remember carbon is 4 away from the noble gas, so it'll be -4. Sodium ion is all the way over on the left. It's Na, and it only forms +1 charges when it has a charge. Bromide, another halogen, -1. Uranium-6, well, they tell you what it is. That's easy. U+6. Phosphide is right underneath nitrogen, so all of those will be -3s. And strontium is another alkaline earth, just like magnesium and calcium, so it's a +2. So now you know how to name all these elements. Naming binary ionic compounds is actually going to be pretty easy at this point. So a binary compound is a compound that only contains 2 different kinds of elements. It doesn't mean 2 atoms. It means one certain number of one element and a certain number of another element, just 2 kinds of elements. And ionic compounds will always be made of a cation that will have its charge and an anion that will have its charge that will be negative. Now, these 2 numbers may not match each other, and therefore the number of cations will not be the same as the number of anions. You have to balance it out. And so you're always going to name the cation first, and then you name the anion. It's always that way. Name the metal or other cation first, and sometimes you need a Roman numeral, and sometimes you don't, and then just name the anion. At no point will you ever say, I have 3 of this cation and 2 of this anion or any other number. You don't need to say that. By saying what the cation is, it tells the reader what its charge is. By saying the name of the anion, it tells the reader what charge that is, and therefore the reader can determine how many of each are necessary. And we'll talk about how to figure that out in a couple slides. So it's very easy with the representative elements, the group A elements, because many of those metals have only one choice. So NaCl, you name the sodium ion, and you name the chloride ion, sodium chloride. Magnesium bromide, MgBr2. You'll notice there are 2 bromines, but nowhere in the name does it say 2. Ionic compounds, you never tell the reader how many of each. You just tell them the name of the 2 ions. Magnesium ion, which you know is +2, and bromide ion, which you know is -1. And the only way to make that compound work is to balance out all the negative charges with the positives, which means we need 2 bromines for every 1 magnesium, or 2 bromides in this case. So that is how we account for the 2 bromines in here. Aluminum fluoride is AlF3. Aluminum has a +3 charge. Each of the 3 fluorides has a -1. So we have aluminum that's providing +3, and we have 3 -1, so that's a total of -3 balances the +3. In this case, potassium nitride, each potassium is +1. We have 3 of them, so that's 3 positive charges. So we need 1 nitride, which is -3, 3 negative charges. So 3 potassiums will balance 1 nitrogen. Therefore, we just call it potassium nitride. But we know the formula based on where the charges are. So the issue comes with transition metals because we have more than one choice. So if you have more than one possibility, you have to figure out what that possibility is. If somebody gives you a formula, you need to remember a couple things. And the most important thing to remember is in any formula, either a compound formula that is a formula unit, as in the formula unit of an ionic compound, or a molecule of a molecular or covalent compound, the total charges, unless it has a charge shown, in which case it's an ion, not a molecule or a compound, if it doesn't have a charge shown, the total charge is 0. And that means all the positives have to equal all the negatives. So you're going to use that information to figure out the charge of something you don't know. For instance, cobalt-3 chloride. Now, we don't know the name initially. We just know the formula COCl3. Well, we know each chloride is -1, and we have 3 of them. So that's a total of -3 charges, which means we need to have +3 charges to balance it. Well, there's only one cobalt, so it must be cobalt +3, and we would write it as cobalt-3 as the cation and chloride as the anion. Lead-4 oxide, PbO2. Lead is +4 because each oxygen is -2. 2 times 2 is 4 negative charges from the oxygens, and therefore we must have 4 positive charges from the leads. W2S5. This is tungsten and sulfur. So we know that each sulfide is -2, but we have 5 of them. That's a total of -10 charges from the anions. -10. That means we need to have +10 to balance it. That means we know the tungsten, those 2 tungstens, must have a total charge of +10. And if you have 2 that give you charge of +10, then each one must have been +5. Therefore, the name is tungsten 5, that's the cation, and it's sulfide. So you always name the cation first, tungsten 5, or cobalt 3, or lead 4, and then you name the anion, chloride, oxide, sulfide. And it's always done this way for ionic compounds, binary ionic compounds. So here are a few examples. COCl3. We already worked through this. Each chloride is -1, but we have 3, so that's 3 negative charges. That means the cobalt must have a +3 charge, so that's a cobalt-3 ion. Well, we have a cobalt-3 ion with chloride ions, and we're not worried about how many there are. We just know it's made of cobalt-3 ions and chloride ions. Therefore, the name is cobalt-3 chloride. NiO. We know it's nickel, but which nickel? And we know it's oxide. So we already know the oxide has a -2 charge, and there's only 1. How do we know there's only 1? Because if there's no number, we assume the number is 1. So we have total of -2 charges. That means the nickel must have a total of +2. So the oxygen would be oxide. The nickel is nickel 2. Therefore, you put those together. Always name the cation first. Nickel 2 oxide. Cu2S. Okay, we know it's a sulfide. Sulfides are always -2. That means our total of our coppers must have a charge of +2. So if we have 2 coppers that are a total of +2, well, then each copper must be a +1. And therefore, these are copper 1 ions. Don't let the 2 in the number fool you in naming them. The 2 there means the ratio of elements. It's 2 coppers to 1 sulfur. It is not the charge of the copper. So this would be, you put this together, copper 1 sulfide. Fe2O3. I'm going to tell you one common name of this compound is rust. It's one form of rust. So we have oxide, as each oxide's -2. We have 3 of them. That's a total of -6 charges from the anions, the oxides. If we have -6 from the anions, we must have +6 from all the cations. That means the two irons must add up to +6. That tells us that each iron must be +3, or iron 3. Well, we have iron 3 and we have oxide. Well, then the name of the compound is iron 3 oxide. And that's how you put these together. Now, I'm going to show you a quick little math on this. I'm going to redraw this and show you mathematically what we've actually been doing all along. If we have a compound like Fe2O3, what I recommend is you put a little notation to yourself that each of these oxygens is a -2. And we don't know the charge of the iron initially. But what we do know is that when we multiply these two numbers, that is the number of negative charges. And when we multiply these two numbers together, that is the number of positive charges. In other words, this times this, well, I'll put a little dot there, must equal this times this. If we disregard the negative sign, don't worry about the negative sign. So if we look over here, 3 times 2 must be equal to 2 times what? And the answer would be +3. Now you have to put the actual sign there. But when you're doing the math, they're going to be opposite signs. And therefore, we know this is iron 3. And we always know the oxide's -2, so we don't need to say anything about that. So it's iron 3 oxide. And that's the math you're going to do for each of the following problems here. You've got a number of problems where you're given a formula and you have to name them. Now I'm going to tell you, you always name the cation, then you name the anion. And in some cases, the cation needs a Roman numeral. So the first thing you should do is just name the first element ion and name the second element's ion, and then worry about whether you need a Roman numeral or not. So right here, we know the K is potassium. Pardon my writing here. And we know the C is chloride. You then look to see that, sorry about that, you then look to see, does potassium need a Roman numeral? No, it doesn't. You're done. So anytime you don't need a Roman numeral, like potassium, sodium, aluminum, and I guess that's it for this list, you don't need a Roman numeral. So here it's just sodium, and the N is nitride. And it's going to be that way all the way down, but sometimes you're going to need a Roman numeral. So I'm going to clear these and just show you the first couple answers. The next one, you know it has a chromium in the beginning of the name and a nitride in the end. The trick is, what is do I need a Roman numeral? And if I do, what is it? Well, chromium comes in many different versions. Chromium can be neutral, of course, all metals can be neutral. But if it's an ion, if it's a cation, it could be +2, +3, +6, and probably several others. But what we know is this: if you don't have a 1 there, write a 1 just to remind yourself there's 1 of each. So it's 1 chromium, 1 nitrogen, and you know that each nitrogen, each nitride, is a -3. So now you know our missing number, X, we just put that in there. We know that 1 times 3 must be equal to 1 times X. Well, clearly that is 3, so we know the name is chromium 3 nitride. If we look at the next one, we know the name is molybdenum something phosphide. I know that's a hard one for people to pronounce. Molybdenum. Molybdenum. Molybdenum and the phosphorus is a phosphide. So we know molybdenum is the first word. We know phosphide is the last word. And we need a Roman numeral because molybdenum has many choices. So we know phosphide is always -3. So we put a little X there for the molybdenum. So 2 times 3 must be equal to 3 times what? Well, 3 times 2. Therefore, molybdenum must be molybdenum 2, and then the anion is phosphide. So it's a molybdenum 2 ion in a certain ratio with phosphide ions. And we don't concern ourselves with how many of each. This one has lead and oxide. And so does number 6, also a lead oxide. So they're both lead oxides. You're going to write lead oxide for each case. But in the first case, we have 1 lead and 1 oxide. And in the second case, we have 1 lead and 2 oxides. Oxide is always -2, so we put that in there. 1 times 2 is equal to 1 times what? Well, that would be lead 2. Must be +2 here. So therefore, that is lead 2. Whereas in this case, 2 times 2 is 4, and we have 1 lead. So therefore, this lead must be 4. That's lead 4. Whoops, I jumped ahead. But aluminum selenide is obvious. Aluminum has no choice. You don't even have to worry about figuring out the charge. You already know the charge can only be +3. And if you look, aluminum we know is +3. Selenium as selenide is always -2. 2 times 3, 3 times 2, everything works out fine. But you don't even need to do the math. And I'll leave the remaining ones to do on your own. I'll pause here. You can practice them, and then I'll show you the answers. Okay, this is gold 3 oxide. The next one you know is an osmium something phosphide, and it's osmium 8 phosphide. A lot of times it's the other number, but not always. So you can't always go by that, by the way. And there's a reason why sometimes it is and sometimes it's not. But please do not use that number directly. You'll notice in the case of these two, number 5 and number 6, you can't use those numbers. Whereas it works here, and it doesn't work here with number 3, it doesn't work with number 5, it doesn't work with number 6, but it does work with number 9, it does work with number 8, and it will work with 10 and 11. So you have tungsten 5 arsenide and tin 4, tin is SN, tin 4 nitride. So it's a clue, but it's not always right, and there's a reason for that. So now we're going to go from name to formula, and this is actually easier, and you'll see why sometimes it worked with that, looking at the opposite number, and why sometimes it doesn't. We have a rule for doing this. It's called the crisscross simplify rule. You have to remember that all the charges add up to 0, and when you're given a name, you're given the names of the 2 ions. You're given, and from the names of the 2 ions, you know the charges of the 2 ions. The cations are just the name of the element, sometimes with a Roman numeral, and the anions are the ides, or they're what we call polyatomic anions, which we have not talked about. That'll be in the next module. Polyatomic anions are anions composed of more than one kind of element, and therefore they're not simple binary compounds, but they go by exactly the same rules. So you balance the charges by adding the subscripts, by going through and looking at the subscripts, but adding subscripts is a little misleading. You're actually crisscrossing the charges to get the subscripts, and then you're simplifying it. And that doesn't make sense to you right now. So let's actually show you an example. For instance, if you know you have iron plus 3, so you were told it's iron 3 oxide. Well, you know that that's iron plus Fe plus 3. An oxide is by definition O minus 2. Well, the crisscross rule says, okay, forget the charges. The 2 goes down here, the 3 goes down here, and we end up with Fe2, O3. And this is why sometimes the opposite number matches the charge. It's because we crisscross. However, in some cases, we simplify the numbers. So 2 and 3 can't be simplified anymore. But if we had something like tin 4 oxide, we crisscross, that would give us tin SN2O4. Well, we can simplify each of these by dividing both sides by 2, and we end up with just 1 tin, so we don't need to write the number, and 2 oxygens. And this is why in some cases the 2 doesn't match the charge on the tin or on the metal. Okay, so sometimes it'll work, sometimes it won't, so don't do it that way. always just do the calculations that I showed you in the previous slides where you're multiplying to get all the anion charges and you're comparing that to all the cation charges. So let's try the crisscross simplify rule. This is for going from the name to the formula. Calcium chloride. Well, calcium is always plus 2, Ca plus 2, and chloride is by definition minus 1. So we need to know how many of each we need to balance. Well, the way to do that is to just set up a crisscross and simplify. So you have the two ions, you crisscross the numbers, that gives us 1 calcium and 2 chlorines, or 2 chlorides, and then we don't write the 1. So it's CaCl2, and then we didn't need to simplify. 1 and 2 can't be simplified anymore. So here are a number of practice problems. Lithium sulfide, for instance. Lithium is Li plus 1, and we can write the 1 if it helps us. And sulfide is always minus 2, so we crisscross that, and we'll end up with Li2 sulfur 1. And that is the answer here. And if we look at the next one, this is one I already, a similar one to one I showed you, tin 2 oxide. So this is tin plus 2, Sn plus 2, and oxide is minus 2. Crisscross, we get tin with 2 of those and 2 oxygens. But we can simplify this to 1 of each, and therefore our formula will just be SNO, or snow. And I'll leave the rest of these to you. Go ahead, practice them. I'll stop for a second, and then you can see if you got it. And with that, we'll start the next unit.